So let me shortly summarize what the objective today is, what we want to do. And let's summarize a bit the end of the conclusion of the lecture. We want to write a little rate transfer model here today, yeah, together. And therefore, I have provided some material. I think the link is now wherever on what kind of place. Yeah, so you can download the data there. It's a zip file, unzip it. You see then directories, and you see 2 Jupyter notebooks. One without solution and the other with solution. So if you're interested in how I solved it, you can have a look in the solution. But I can imagine it's also nice to do it yourself and get some experience, right? So overall, you need to have an environment with some packages, some very simple packages. NumPy you need NetCDF4, or if you want another NetCDF reader like Xarray, but I use NetCDF4 in the libraries, the plotting library. I'm pretty sure if you have worked with Python, there's no way around that. And SciPy. If you don't have SciPy, then you cannot do the last step, the last task in the notebook, but you can even do a lot of other things, right? Good. Having said that, I think it makes, so please download the data, unpack it. I would like to suggest that you work in groups of 2, 3, 4 people, discuss it, find a solution, and do something, because it's this lecture, you know, it always sounds nice, and if you have to do it yourself, then it's much more difficult, and then you really see what you understood and what not. I will walk around, you can ask me questions, we can also discuss it here on the screen, the prototype solution, and that is a bit the setup I had in mind. I want to give you a short introduction what we will do, because not everybody followed the rate of transfer course. The rate of transfer lecture was about an equation which provides us what we call the radiance. The radiance I was defined as an energy flux. So we have to describe the radiation that we want to simulate with this Jupyter notebook as an energy which goes through the surface over a certain time in a certain solid angle and in a certain wavelength domain. That's the quantity that we want to simulate, right? And what we want to do is that we have a model atmosphere which tries to capture what we see outside. Nah, it's raining now. We assume clear sky, bright weather. And what we do is that we assume a stack of layers, n layers, whatever the number is. We have a sun which illuminates the top of that model atmosphere. And you will get a solar spectrum. So the light which comes from the sun is in a file, you read it in. And then you simulate the transmission of the light to the surface, taking into account that there is carbon monoxide and methane vertically distributed in the atmosphere. So there's a file, an atmospheric file, which gives you the concentration of CO2 gridded in different layers. We do get what we call the cross-section, so how much light a molecule really absorbs in a layer. And you have to calculate the optical depth. And then you can calculate at the end the transmission function through the atmosphere of the solar beam to the surface, you know, then the amount of radiation at the surface. You simulate the reflection at the surface using the Lambertian albedo that we have discussed. And then you go back the way up and you simulate this, you calculate this transmission as well, and then you have your signal at the instrument level. So then you see the spectrum which falls on the instrument. And in the last step, because that's what I said at the beginning of the lecture, you may remember I said the radiance can actually not be measured. It must be something that the observation that we simulate from the radiance. And that's what we will do in the last step, where we say the instrument has a certain sensitivity to the spectrum, and we convolve the physical spectrum with that sensitivity function to get the real observation. And then you have an observation, and it is measured, for example, by Tango. You've heard about Tango, I heard. It was presented. By the way, I'm the PI of that mission, the principal investigator. So we measure in the 1.6 micrometer band. That is the band that we will simulate. So we will simulate a measurement as it will be measured by that mission to infer finally from the observation CO2 and methane, right? So that's the whole idea, yeah? It's a tough program. The first thing is please check that the packages are there. Yeah? Can we do that first? Make a round and that you check that packages are properly installed. And if that's not the case, and you know, I'm honestly, I'm not a Python expert who knows to install packages on Windows. I work on the Linux. I ask your neighbors, try to communicate with each other, find a solution, or build groups and work on the laptop where it works. Yeah. So I really want to go with you through the content, preferably, and not through discussing computer issues. I hate computer issues. So.
I just on my hotspot now. It works. I was fast. Because everyone else is loading up this.
Oh, now you're downloading it and the internet collapses. Or...
I've got it.
Oh, good, good.
I was watching.
But
if I click on the link, this is
how is there? Then you need a password. That's my.
The second, click on the second link and the message.
oh,
Yeah.
This one.
The password is just tutorial with the D in caps, and that's it. But you don't get a password prompt.
no.
Try to click on it again. I had to click on the link twice.
Oh, okay.
There was actually a password.
It's probably that. Oh yeah, and here it says password tutorial. I can do that. Okay, I have to
I
click
simply
twice.
don't remember it anymore. I just did that so you can have fun and everything.
You invented, so you-
Yeah, I did.
Yeah. I'm surprised, but it's I was sure. But it's
Do you all have access to the file? How is it going with the packages? Oh, that sounds brilliant. Just give me a sign when we can start to discuss the different tasks. You're fine, you're fine, you're fine, you're fine as well. Oh,
Mostly fine.
mostly fine. You're still
Not yet.
not yet. I have the idea that you're fine. Not yet. You have the internet issue. You okay? How's it going with you guys? You're good? Come here.
Also the solutions. It's practical. And
You're fine?
Yeah, it's
Yeah.
downloading. but
It's downloading? Downloading. Downloading, downloading. Okay, it's only a question of time. And you're already familiar with Jupyter notebooks? NumPy, it's no problem for you, and NetCDF? Perfect. Excellent. So let's wait another 5 minutes and then we start, yeah? That's funny, actually. I thought they had some other picker point. So they linked actually to my own cloud link. That's my link. So, and I thought they downloaded it and put it somewhere that you have easily access. Yeah, that's it. I thought, what password should I use? Oh, tutorial. Oh, okay. Oh, fine.
I have a question actually
Sure.
on the cross sections.
Yes.
I don't know, but
No, go ahead.
because you explained it as product between the line profile and line intensity.
Yes.
So as I understand the cross section, I understand the line intensity, but I don't really understand the line profile. So with what do we? Because the line intensity, we see the dip in the.
The line intensity is the integral over the full line. So
Yeah.
how much light is actually absorbed.
Yes, this I understand.
All right.
The line profile.
Yeah.
What,
Yeah.
what does that? Which
Yeah.
type of?
Yeah. Profile. Profile is maybe not a good word for it, but what it means, we discussed these two level atoms. You remember that in the course, in the lecture? And the point is that the upper energy level is not well defined in the sense that it has a finite lifetime. And if something has a finite lifetime, the energy is not sharply defined. There's an uncertainty on top of that. That is this Heisenberg relation. So actually, sometimes it exists there, sometimes there. So if a photon is absorbed, it can have a transition there, or there, right? But this one is less likely. This is the most likely one. And this is again less likely. So if you see that in an absorption feature, it shows up like this. That is the most likely one. And other wavelengths become less likely. That's the profile. Yeah?
The profile will take into account the 3 points, or
Oh, just as a continuous function. This the actual lifetime is not a single number. Sometimes it lives a little bit longer, a little bit shorter, and it's a continuous function. Yeah. So that's how molecules behave.
But then
It's weird, eh?
the profile, it's similar between other molecules.
It depends on what goes in. I think, the shape it's always very similar, but sometimes a bit wider, a bit more narrow. Yeah. Good. Okay. I hope you all have something on your computer. The first thing I want to ask you now is import the packages. I think it's even already mentioned there, if I remember right. And then use the netcdf function dataset. You see we have imported it from netcdf dataset and read in the data from the file xsections, which is in the data directory. Yeah. So those are the cross sections we discussed. If you haven't heard about cross sections, it describes the wavelength at which a molecule absorbs light. Yeah. So if you have a molecule like CO2, it has very distinct wavelength where it absorbs light and others not. And you can plot it, and then you see this absorption cross section as something like that. Yeah. And this is in that file. I will do that myself as well. Read in the data.
Ja, je beelden van meer dan dat. En als je daarop specifiek gewoon is dat een dit of een?
I don't know if you're familiar with netcdf. I think it's a very handy data format for us. And when I started, I've used ASCII. That was a disaster. Yeah.
You should open the solution one.
If you want, you can open the solution, but we will go now stepwise through the tutorial.
The point is to find it yourself, I think.
Yeah, the point is that you find it, you try to solve it yourself. Yeah, that is for discussing here. I won't type it myself again. If you read in the data, please inspect what is in. What I do is here in this that I use then the print statement. We have two groups, atmosphere and cross-section. In the atmosphere group, you find then the vertical concentration of CO2, of methane. As we do see here, that is then an array of the air density in the different layers that I just explained. We have the methane density vertically sampled, the CO2 density, water vapor is in the atmosphere, which absorbs in our spectral range as well. We have the layer temperature, pressure, a lot of information about the atmosphere, auxiliary information. So just inspect that you have this data, then you can print also the cross sections, which are as a function of wavelength, the XU2 cross sections, the methane cross sections, and the water vapor cross sections. So these three species, they do absorb light. Do you manage that? Yep. Okay. Also fine. Did you? Yeah. You can even plot the dimensions of these arrays. It's quite interesting to see how they are set up.
I think I can directly see the plot in Telegram.
Yeah. 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 All right. Good. You know, normally I give a lecture at the university, and then we are now at the end of the first day. Because it never works that they can install a Jupyter notebook. Good. The next thing I want to ask you is select the CO2 methane and just take one species. So select the cross-section of CO2 first, methane or water vapor, and consider the absorption line. So something like an absorption line is the cross-section. This is then a typical absorption line, yeah, as around the central wavelength. This is the one for CO2, that's for methane, that's for water vapor. And then plot the absorption line for different altitudes. Why do we do that? In the lecture, I explained there's a line broadening, so that the lines get broadened in the atmosphere because of collisions between molecules and because of the Doppler effect. That was subject of the lecture, and I just want to now show you how that looks in real life. Yeah?
Inderdaad, dus toch.
Ah, oké. Wat is observe? Observe, die vraag is dan dit is
cross section. And that is density. So there is absorption. That is a cross section. Absorption cross section.
And then I take all the out. I don't understand.
Five.
Ja,
Ja, ik wil gewoon weten, dus gelijk aan de. Ja, maar dat is niet waar. Ja, dat is even gewoon buiten.
Ah, I see.
Als dingen opgegeven. Als, ja, dus die. Ja, dank u. Sorry. Goed. Het is de laatste dag van de week. Hè? Ja, zodat. Ja, natuurlijk. Dank u. Ja, nu krijg je natuurlijk wel van.
Since that makes it probably
Yeah, that looks pretty good. Now you only have to zoom in. Hey, you heard the lecture? No. Yeah, you are. Yeah. Those are the two CO2 branches I showed, right? That is one vibrational mode. That's the other vibrational mode. And if you zoom in, then you have the individual lines. So zoom in on one line and see how that changes when you use different altitudes, going from a high altitude to the surface. And just select, I do that in step of 5 indices, because otherwise you get too many lines. And then you see nicely how these lines get broadened.
A model for the line cutting as a function?
I already calculated that for you. So that's in the file.
Okay.
Yeah, and now if you do that, then that take a while. Yeah. Okay. So it's a lookup table. When you see the file, the cross section, that's a function of height and of wavelength.
Okay.
And the height is there. I have taken into account the broadening, the line shape, how it changes with pressure, and yeah.
Why do you have different lambda deltas?
You have these two energy levels where you have a transition of molecules, right? It's a transition between two energy levels, and for sure, and that difference determines where the line is positioned in the spectrum, right? And that changes from molecule to molecule.
But that explains why the lambda center is different.
Yeah.
And why the delta.
Which delta you mean?
Lambda delta.
Oh, what do I do with that? Where does it go into the lambda? Oh yeah. I don't see. Yeah, exactly. It's just, the width of a line is also changing a bit from molecule to molecule,
Okay.
so that you have nicely the line within your picture.
It's somewhat arbitrary.
Yeah, I have just chosen it to have nice pictures. Yeah, you can. Well, if you take one numbers, maybe for one species, they're so narrow that you don't see anything, right?
Oh, that's why I was confused. I wanted to put the altitude here, but we're putting the different lines or the different altitudes.
Yeah.
I can say that.
Yeah.
Yeah.
So is this what we have? Select the cross section.
Yeah, I need my glasses.
Oh, sorry.
Reading glass. Oh, can you enlarge it? Yeah.
Oh, yeah, okay.
Yeah. Oh, yeah, that
Or is
is.
that not what you're doing? Because I'm just looking at the variables here,
Yeah.
and it says select an absorption line at this. But I'm not sure where to look for it.
So it's in the cross section, right?
Yeah, which is this.
So you take that one. Why do you call it? Did I call it SW?
There's one wavelength.
Yeah.
That's maybe what you're going for.
No, and also the cross sections.
And there's
per
one
species.
cross section CO2, one cross
Methane?
section methane.
Okay, exactly.
So that's what I'm getting here.
Exactly.
Okay.
And it's just to, yeah, I think it's a kind of pointer that you are doing here to point to that variable
Yes.
later for the plotting.
Yeah,
Yeah.
like here.
Yeah.
Okay.
Yeah.
That's good.
Okay, and then and if you look at the dimension of that array, I think it has in the first wavelength and in the second altitude.
Or CO2, for example?
Yeah. Yeah.
It says the array. Oh, but it's because I chose the values only. So if I do this, like this.
Yeah, exactly. So those are the wavelengths, and that is the yeah. So they're highly sampled.
And they're already at the correct wavelength, right?
That's your choice. It's a
Oh.
physical spectrum. There's not a correct and a not correct one.
Sorry.
Yeah,
Okay,
we're just it's actually a continuous function in reality, and we calculate them at 30 levels.
Okay.
And that means at
Vertical
30 pressures, at 30 temperatures. And they are also given in the atmospheric variables if you are interested in. Yeah? Yeah?
Yeah.
How is it going?
I cannot see currently the board, so I just directly check each variable through this app. So I see like what you show is the wave case.
So as the amplitude increases,
Like the layer height absorption. So
And can you make a plot like that where you do see how the line shape changes with altitude? I'm not sure if I see it here.
so it's like this, like the x-axis is the layer and the wavelength is the absorption, or
Yeah, but now you're not zooming in on one particular line. This, I think, is the full spectrum, isn't it?
yeah, it's full spectrum.
Yeah. So and if you zoom in on one particular absorption line,
Yeah.
you see how it changes with altitude.
Yeah, that's much clearer. Can I see
Yeah.
a little bit clearer?
Yeah, sure.
yeah.
Mhm. So who already could manage to plot a figure like here? I mean, the format, I don't care, but you managed? You're close? How's it going here? No?
No,
No.
because I selected the wavelength, but you didn't want to select the wavelength specifically.
I-
And
No,
then
no,
thought
It's a
because-
range, and I only manage that via the plotting setting that I look at one line. Yeah. And the cross section, you probably have seen it. It's a 2D array. The first dimension, that is wavelength. So I think, I don't know, 20,000 points. And the second one is altitude. So you select a few altitudes and then you plot one single line and see how that changes with the different altitude levels. How's it going there? Exactly. Beautiful. Yeah. What is this?
Was the H2O I subtracted the wavelength no.
You can do that in many different ways. You can subtract the wavelength, but you can also plot it and put the range around it. I don't care.
Okay.
Just select the window where one line is in and plot then the cross sections for the different.
Okay.
Yeah.
But then that's to center it, the lambda.
Yeah, exactly. Yeah, but you can do it differently. It's not that I have the only solution here. Yeah.
All right.
Yeah.
The fastest thing to do would be to first slice out the wavelength range you want to see and then only plot that. But the other way to do is just to plot the whole thing and then zoom in.
Oh yeah.
Yeah.
Excellent.
Yeah.
Okay. Then I'll plot the other ones too.
Yeah.
Water.
Yeah, but what I really, yep.
Yeah, excuse me.
Sure.
I want to ask how do I interpret this cross section? So you mentioned it's kind of the wavelength information.
That is the wavelength information.
Yeah,
And that is, you may say, the probability that light is absorbed at that wavelength.
opportunity,
The probability
of the
Yeah.
light that can be absorbed by the
by the molecule.
by the CO2 molecule.
Yeah, you have some light coming in. It meets it hits a molecule, and then it's the question: is the light absorbed or not?
Okay.
Right?
Yeah. Yeah.
And the cross section tells you if the number is large.
Uh-huh.
Oh, yeah, the
Yeah.
chance is pretty high that this light is absorbed here.
Yeah, so it means that at the top height, there will be more probabilities of
Absorption.
absorptions.
Yeah,
Yeah. Okay.
Exactly.
Okay, so that's kind of the this. What's the meaning? The meaning of this Y line is kind of the probability of the
Yeah, actually, it's
the absorption.
yeah, it is something. It's actually given in the units are in a centimeter square. It's an effective area, and the larger the area,
yeah,
the larger the chance that it's really absorbed. But this interpretation is not fully physical, but that is a bit the picture you may have in mind.
yeah, because I saw its number is very
Small.
Yeah, it's like a.
But do you know how many photons we'll get from the sun? Huge number of light coming in. So we are playing with huge numbers and very small numbers,
Okay.
Yeah.
Okay.
and CO2 is also not a strong absorber.
No.
Yeah.
Okay.
Yeah.
Good. Thank you.
Sure. How's it going?
It's going.
It's going. That's good.
We go. I have yeah. So then I'm trying to figure out how to actually zoom in.
Yeah, you can do that with the range of your plotting routine. I think it's XLim I always use, but
So that
Yeah.
we need to.
exactly, that's perfect. That's perfect. Doesn't have to be exactly that figure.
Yeah, I mean, that looks very nice.
Yeah, but that's not important. That's not important. But it's, I also want to see that you understand the data structure. How's it going here?
Trying to get the value of the wavelength, trying to get the index of the wavelength.
Yeah, but you can easily just change in your plotting routine the range. I think it's XLim, if I remember right. XLim. XLim. Blah, blah, dot XLim, and then you give two numbers and then you zoom in. That's pretty simple. Otherwise, you have to deal with all these indices. You're getting crazy, Yeah. How's it going here?
Yeah.
Yeah, we work on the solution.
That's fine. But do you understand it and it runs?
Right. Yeah, it
Yeah.
runs. We try to
And
understand.
that's the funny thing, when you're in the can't stand. When you're in the atmosphere, you see that the line is pretty narrow at high altitudes. But then you have collisions of molecules.
That means that in the higher altitudes, the molecule less bending together, and then they will have a.
No, the meaning is a different one. The density of molecules increases at lower altitudes. And so the chance that you have a collision between molecules is higher. And that means the lifetime is shorter. And that means that you get an uncertainty in the energy level definition.
Okay.
Yeah, that's what we call pressure broadening or collision broadening. And then physically, there's another effect that is Doppler broadening that takes a bit higher up in the atmosphere. And I've calculated these cross sections for you already, keeping this in mind. But we see it in the data. Yeah. Good. Good. I do see.
We didn't follow your lecture before. Then we asked the ChatGPT to interpret this.
Really?
We learned. Yeah.
Oh, ChatGPT, it's amazing.
We learned something.
How's it going? Excellent. That's good. Yeah. And you understand the figure also?
Maybe I have a question. Why does it like decrease? This what does this?
Okay.
This is the on the y-axis. What is the?
The unit is actually it's an area. It's cross section, but I wouldn't overinterpret it. It's in principle the probability that light is absorbed.
Okay.
Right? And you have to multiply that then with the density of molecules to get an optical property along the light path. Makes sense, right?
Yeah.
So that is really and why it's broadened. The integral over the curve must be the same. But because the lifetime, as we said, the lifetime gets shortened, there's the chance that also light at different wavelengths can cause this transition.
Okay.
And that's why this line, as the area is the same, the maximum goes down and gets broader.
Okay.
Yeah?
The integral is the same.
The integral is the same. That is, the integral is the line intensity, and that is all the same. Okay, I think we can go on.
You see actually multiple lines, and you want to focus on one line, so you need to make your wavelength range much smaller. That's all.
The next thing is, now we understand a bit the cross sections, but we have to get the optical properties of the atmosphere, we have to multiply the cross sections with the number of molecules we have in the atmosphere, yeah? Makes sense, right? So go into the group atmosphere and simply plot the profile of some species, which here is CO2, methane, and water vapor. See how the concentration changes with altitude. Yeah?
So I've plotted here the CO2, but how do you know which temperature coincides with which?
I've calculated that for you. That's a lookup table simulated for the atmospheric conditions in the atmosphere group.
So it's an atmosphere.
Yeah.
To combine them.
Yeah, it's one.
If you want to put a label on there, yes.
Yeah. So in principle, for each observation, you have to regenerate cross sections for the. Yeah. And I try to do that. Hope it runs. It's already given at the layer center.
So we have levels, the interfaces.
Oh, at the layer.
But at the center.
At the center. I think so. Yeah, I think it's given at the layer center. Because the idea is that the layer is homogeneous, so the density is constant within that layer. And can change from layer to layer, and then you get the profile, yeah?
Height is in meters.
Probably. Not put the numbers on the sheet. I think it goes up to 30 kilometers. And let me know when you have plotted already the CO2 vertical distribution. What I do is I plot as the CO2 concentration on the x-axis and altitude on the y. That's a very common way. Bit weird, actually. As a function, it should be just the other way around, but that's how we do it in atmospheric field. And then you see nicely the profile as a vertical distribution. And please let me know when you already have plotted the CO2 profile, because then I want to discuss a few things.
Do you also have the temperature in your figure?
In this figure not, but you can plot the temperature as a profile as well. And I hope then you see the tropopoles at 10 kilometer, I hope. Actually, I'd never plotted it. But you see it?
Yeah, but it's not that clear because in this case you have that here it's almost constant, so the exact height is a bit harder to do.
Yeah. So what you actually get here, that's what we call a standard atmosphere, right? So in that field, we agreed to use certain standard atmospheres to compare things, and I just used the US standard. The year, I don't know. And I scaled, honestly, I must say, and I scaled the CO2 concentration to a more realistic value. Because in the US standard, I think it's at 350 ppm. Okay. And I hope it looks differently. So don't look at that picture yet. Oh.
It looks very different.
Excellent. Yeah, I will talk about that in a second. So you really see a huge increase at low altitude.
Oh, I need to avoid the air density. Oh, sorry.
You're still working on that. Good, that's good. That's different, but I will show you in a second why.
Oh, I was like, oh, that's not the same.
No. It's different, but it's fine. It's fine. How's it going? That's fine. And you already heard it. Yeah. But that is the file, okay? But that's not the density here. If you plot the density, if you look what you plot, it's a ratio of the sheet. Yeah, and change that, and then we discuss why this ratio makes sense.
Okay.
Yeah, because that's what I want to do as next step. Yeah. Yeah, I just comment it out and remove it. How's it going here?
Not so good.
Not so good. Oh, that looks.
I get straight behind here. Because
I need my class. That's too small for me. I just come back with my reading classes. Yeah, that's okay. So that's the annoying thing getting older. But you're not plotting as a height, as an altitude. You plot simply.
I mean, at one level, right? Oh yeah. I got mine.
Yeah, I do believe that this dimension is 30. The first, I don't know. What is that?
This first dimension is the wavelength that goes to 200,000 or something.
Oh yeah, those are the cross sections. Okay. Yeah, sorry, I didn't know. You're plotting now the cross sections.
Yeah, it's like yeah.
That's okay.
It goes this like this.
Yeah, that's okay.
Yeah, so it was. Which, oh,
That's fine.
yeah. It gives cross-section.
Yeah, those are the cross sections, and what we're discussing now, that is the atmospheric concentration. So how much CO2 is in the atmosphere,
Okay.
and that changes with altitude, obviously.
This is proper. Yeah.
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 Good.
Is this the CO density?
Yeah.
Yeah.
Yeah. Go up. Yeah. That's an artifact, by the way. Yeah.
But what's happened here?
Oh, it's just an artifact in the
Ah,
data
okay.
because I combined some data sets and I made a very
okay.
little bug there.
Okay.
But it's not so important. It's anyhow so little.
Yeah.
So, yeah.
Yeah, I have a question.
And just come on your side. Yeah.
What does this ratio mean?
It's very. I want to discuss that. Plot it first without.
Yeah.
Yeah?
Plotted and I found the CH4 is kind of confidence. Yeah, missing.
And that's the ratio.
Yeah.
And if you remove now the air density and plot really the density of the molecule.
You mean the CH4 density?
Yeah.
Okay, then will be different. Oh no.
Yeah.
Let's see. Oh.
And we want to first get that profile. Okay, I think we continue now because I want to discuss. Yep. I see most of you managed. And these classes. So you've seen the profile. That's your CO2, and it looked a bit like this. Right? Yeah, CO2, has an extremely long lifetime in the atmosphere, right? Actually, there's no real chemical decay. There's no, maybe high up in the stratosphere, there's some dissociation, but in practice, CO2 stays in the atmosphere. Maybe it mixes in the ocean. There's some uptake from the biosphere, but also some release, but there's no really a loss mechanism of CO2. So CO2 stays, let's say, forever in the atmosphere. And that's why we say this CO2 gas is well mixed, right? Because we have mixing process, we have turbulences in the atmosphere, mixing between layers, particularly in the troposphere, a lot of mixing. So we expect that CO2 is well mixed, particularly when we're not close to a source, right? Yeah? But what does that actually mean? Because the air density decreases when we go to higher altitudes. So it's the relative fraction of CO2 which is interesting. So if that is constant, we speak about a well-mixed gas. It's a relative contribution compared to the air density, right? And that's why we in this field always talk about mixing ratios, which is always the ratio of the density of a trace gas divided by the air density. Yeah? And typically for CO2, we give that in ppm, parts per million. It's like percent per million. So you have to multiply that then with 10 to the minus 6 and
you're exceeding the.
Oh, yeah, please go ahead. Yeah, it's fine. And that's why we talk about ppm. So for CO2, 400 mixing ratio. Yeah, that's the typical value. When you read the news, that's the number you get there. Yeah. So if we divide it now by the air density, then you get a profile. And you will see that in this particular case, for CO2, it's very nicely around the value of 405 ppm. Currently, we are, I think, somewhere above 415 already in a typical background concentration because CO2 increases, right? So when you have done that, and that's what I did here, right? So here I already divided by the air density and multiplied it with 10 to the minus 6 for CO2, 10 to the minus 9 for methane. That is called then ppb, right? Parts per billion. And then you get values of 1,800 ppb. That's a typical methane concentration. Yeah? So that is our terminology in atmospheric physics and chemistry as well. Clear? Right? Now you know why I divided it. It's just the units and the way we talk about data.
For ease of use, paper, the atmosphere, it's the layers are always as thick.
Yeah, yeah, we just use that.
So I
that
can just
that
multiply by value
and
with the optical dependence on.
probably maybe you should talk then what you actually do. So what do we have? We have the cross sections, we have the density. Yeah. And what we then do is that we calculate, let's see what the next task actually is. So not that I'm saying here wrong things. Yeah. Okay. Okay, we go to task 6 now, right? And we really want to calculate now the transmission through the atmosphere. First, we calculate the optical depth, which is defined as an integral over altitude, cross-section times the density of that species. So for CO2, you take the density, you multiply the density with the cross sections, you take the layer height, the thickness of that layer, it's 1 kilometer, I believe, and then per layer, you calculate the optic depth and you sum up the different layers, right? That's what you do. So you calculate that for per species, and then you can calculate the transmission of the atmosphere per species, right? Which means how much light is actually transmitted from the top to the bottom in a vertical line. Yeah, do that, and then plot the different transmissions. And then you see where the atmosphere is transparent and where it absorbs light, right? And which species absorbs light.
Maybe I misunderstood that you said calculate the optical thickness per species, but it's just the same. It's just.
We have CO2,
Yeah.
we have water,
Yeah.
and we have methane.
But if I look at there, does it?
That's the X. X is the species. X stands for CO2.
Oh, yeah. Oh,
X is my species variable.
okay, thank you.
Yeah.
So it's typical, then it's a typical CO2 profile.
Yeah.
This.
Yeah.
What is the geolocation, or is everywhere like this, more or less?
More or less, but not when you are close to a source. Assume that you have a power plant outside, coal-fired, right? They emit CO2. So locally, you get a small enhancement.
Okay,
On
so
top of
this
this is a typical background situation.
Ah,
Yeah, so we are far away from emissions and only see the well-mixed air, which was mixed over the years, and that is the atmosphere. And you know, close to a source, it can be much more. Maybe a factor of 1.
You would see like a bump and then it goes down, or how would what is the profile of the CO2 in a source?
Yeah, if you have a power plant, let's use that example. It emits at a height of, what is it, 100, 200 meters, not more. And this emission plume stays then in what we call the atmospheric, the planetary boundary layer, right? So you have the boundary layer at 1-2 kilometer, and there it's well mixed, but it takes some time to exchange air between the free troposphere and the planetary boundary layer. This time scale is too long for a bloom because then it's already so much diluted that you won't see that. So it stays mainly in the boundary layer. There you have turbulence and it may rise by a few hundred meters. And that's a bit like what you see, the moisture, the water vapor at the stack, right? That's exactly what CO2 does. Yeah.
Okay. You want to see the profile of that meter? Did you see that?
Yeah, I don't know if I should.
Okay, this is even more boring.
Yeah. Okay.
I did the same for the CH4, but it's a straight line. Or
Yeah, it's also, you know, methane lives for 12 years in the atmosphere. It's also pretty well mixed. Yeah, 12 years. Huh?
This is 1.800, can be?
It is,
Molecule per, maybe it's
yeah, 1,800. Yep,
1,800.
ppm.
But it's really a straight line.
Yeah, I just honestly, I've chosen it. Yeah, it's a bit boring, I must say. But honestly, above I think 12 kilometer, you see decay in methane. So the stratosphere, there you have chemical reactions and the loss of methane, and you do see really in a profile a loss. So I didn't account for that, to be really honest. But 1800 is a realistic value for the troposphere, this mixing ratio. Yeah.
En wat moet je dan doen met die brandseerpuur?
Relative amount of the molecule.
Nou, dat moet je op potten. Ja, interesting. Wat zijn alle kleuren? Alle kleuren is een soort van altitudes.
Does it work?
Oh, I'm trying to figure it out.
Okay, still okay,
Yeah.
fine. You know what to do?
I'm just looking at the solutions. This one? Yeah, no.
It's beautiful. Yeah, that is the total one. Yeah. So actually, you know, when you look at the spectrum, first of all, only light is missing, right? And that's what you see, and then you see the different contributions. That's CO2. Also, that's something we discussed in the lecture. Good. Also, the different vibrational bands. So that's the different vibrational modes. You know a bit about vibrations? Okay. Because you're already looking at that, I can tell you a bit of more details. You have, it's a symmetric molecule, COO. Now, it can vibrate like this, or it can vibrate like this. Those are different modes, and they have different energies. And this is something you see here in these groups. Those are different vibrations of the nuclei of the CO2, right? And these are then, have you followed the lecture? No. Yeah, okay, then each line that you see here, we do know a molecule, there's the electron, and the electron goes from one energy level to the other, right? And that is absorption. But for molecules, this is much more complicated. And for CO2, it's such that the electron is not allowed to do this. So the transitions of the molecule are determined by the kinetics of the nuclei. Right? And the nuclei can do two things. It can vibrate and it can rotate. And that's the kinetic that we use, and then we build up solutions of the Schrödinger equation finally. And you see here the effect of vibrations, and each line belongs also to a difference in the energy level due to rotation of the molecule, because it's quantified, then you get different in these angular momentum quantum numbers, J. I don't know how much you know about molecular physics, but then so for each of those you get a line. Yeah, and that's what's that's happening in the atmosphere. All these lines, right? And that's what you see here. Yeah. Okay, and then you go through those, and then you see methane absorption. Right?
Yeah.
Methane is much more complex as a molecule. So that is a different branch, that is a different vibrational mode. Everything goes, yeah, you know, can imagine those are CH4, it's 5 molecules. They do crazy, yeah? And that's also what you see, yeah? Spectra of linear molecules are always nice, and other molecules it gets a mess. And water vapor even more. Yeah, water vapor is completely weird. But those are now the absorption lines per species, and if you multiply them, you get the total.
Yeah.
Right. But that is the transmission along a straight line from top to bottom. And in the next part, we have to take into account that the sunlight goes slant through the atmosphere, so it has a longer light path, and the observation is also slant. And this geometry of sun and satellite, we need to account for. The light path is longer, the absorption gets deeper, right? And that is the next part. You may have already a look at that, yeah?
Okay.
Yeah?
I have one silly question.
Sure.
So I'm not having a background with the physics. I'm from the computer science. So my question is that what kind of the analysis, applicational analysis that we can derive from this kind of data?
Oh, you know, you measure something. You have a satellite.
Yes.
And it measures a spectrum.
Mm-hmm.
But we don't know how much CO2 was in the atmosphere. We don't know how much methane was there.
Yeah.
We don't know how much water vapor. All that.
Yeah.
No clue. So now we have a model which simulates that observation under the assumption we know it. Right? Having that, we can compare it with the observation. It differs.
Okay.
And then there are ways to adjust the input in a smart way to bring both into agreement. And that's how we interpret data.
Okay.
So you always have a model which simulates the observation under certain assumptions. We vary the assumptions to bring them into agreement. And then we say, okay, this is the information we could extract from the observation.
The model you explained before is a kind of physical model?
It's physical.
Okay.
Yeah.
Would it be possible to, let's say, generalize into like machine learning model that is based on the data?
Depends on the problem. Depends a bit on the problem and on the requirements you have. You know, for CO2, we want to know that with 0.1% accuracy. And that puts very demanding requirements on your AI application.
Yeah.
And on the training set. And on, you know. So there are things you can do, but it's much more difficult than when you're having a species where you with 20% accuracy, then AI is simply to use because you can accept large errors. Yeah. But still, it's ongoing because we get so many data in that we need clusters of resources and people complaining about that. You have a C2 mission which requires 1,000 cores, you know, and then people not getting really happy. It's really getting a cost factor. Yeah, energy. Yeah. But AI also costs energy. So good. Questions?
I think we are almost.
Good. That's good. Good to hear. How's it going here? Straight line.
Yeah. I didn't take the ratio.
That's the cross section.
I was just looking at the columns here too.
Yeah.
Time. Yeah. I think this would be the. Yeah.
Yeah, that's the column. But if you want to go now to a spectrum, you have to use the density itself.
Yeah. So this gives me the density.
Yeah. Without the sum. The sum is already in operation. Yeah. On the object.
Yes.
So you should remove that. Then you have your classical array.
Yeah.
Which is the density.
Yes.
You have to multiply that with the cross sections at that layer.
Okay.
And the thickness of the layer itself, the D set.
Yeah, so I get the thickness. I think this is the thickness.
Yep.
Yeah.
It's only positive.
Yeah, like I did it.
Yeah.
So So this gives the column density, right? Like, I sum it up. And then I multiply with it and then the thickness.
But the cross sections are missing here. I don't know what you want to do here. You're calculating now the column.
Yes.
But you have to calculate now the optical properties,
okay.
and therefore you have to multiply it with the cross sections. They tell you how much one molecule, how much light it absorbs of a certain wavelength, right?
Yes.
So you have to multiply that, and from that you can calculate then the transmission. It says how much light goes through the atmosphere.
Yeah.
Yeah?
Yeah.
Good.
Thank you.
Just want to go there. Yeah. So sorry, I've never been here. So,
now it's episode 6.
Yeah.
And I just finished this one.
Good, good.
Yeah.
What you have to do is that you have a cross section.
Yeah.
Just use that here. A cross section that's called X CO2 for a certain wavelength, a certain height. Yeah.
Yeah.
You have to multiply it with the density at that height.
Yes.
Times the thickness of that layer.
Okay.
And that is what we call the optical depth. This comes then in the exponent,
okay,
the transmission function minus,
okay,
and then you see how much light is transmitted. Sure.
Yeah.
How
Trying to have the absorption for the CO2. But, trying to do the delta Z also to integrate.
Yeah, there is this function NP-diff.
Oh, okay.
Then you don't have to do that.
Okay.
The NP-diff already does the difference.
I mean, in this case, they're all the same thickness, right? But technically.
Technically, it's NDiff, but practically it's 1000.
Well, the annoying thing about every diff is means you have one less.
Yeah, then I think you have to use you're right. Yeah, you're right. Yeah. How's it going?
Yeah, but I do treat this in the tutorial.
Yeah,
Even
yeah.
Fly, I don't know what's
That's
going
okay.
on at the
Yeah.
beginning, and
Yeah.
I just directly see that.
Yeah. But it's good if you can follow it a bit.
Okay.
Yeah. Because of time, I wanna go on because maybe you don't manage it fully. We only have 20 minutes left, that's why I'm a bit pushing now, and I really want to show you the final results because the idea is still we want to simulate an observation, right? At the end. So what do we have? We still need the amount of sunlight, right? We don't have that yet. And that's what we do here, that we read in the data from a file. It's what we call, we assume the sun is constant, right? Not really true. The sun also changes in time. So we read in the data from a file and we convert the units. That's a bit of, I like to work with photons instead of watts, but that's a matter of personal preferences you have. And the funny thing is, if you do so and you plot then the solar spectrum, where you see all the absorption lines from the solar atmosphere, by the way, and emission lines there, you see huge numbers because I think you'd said, oh, these cross-sections, these are really small, 10 to the minus 21. But you will see how many photons we have in the atmosphere from the sun. So, and that is the amount of light, right? So that makes sense. And then we interpolate it to the spectral grid of our cross-sections because we want to have it on the same spectral grid. And then we have the solar spectrum, right? And maybe I want to then explain the next box. So you have the amount of solar light. We have then taken into account the slantness of the light path. You know, the sun has a certain slantness. What we calculated so far, that was the transmission vertically through the atmosphere. But finally, the sun has a slant light path through the atmosphere. So we have to enhance the light path by the cosine of the solar zenith angle. That is the geometry, right, of that light path. Quite straightforward. we have to do the same for the observation line of sight, modify the transmission, multiply it with the solar spectrum, account for the surface reflection, and finally we have the spectrum at the entrance telescope of our satellite. Right? Go through whatever you want. Maybe you are ready so far that you can do that. You can also look in the solution how it works. And then 10 minutes before 3, we will talk about what we have to do to account the instrument in this simulation. Because now it's the light at the entrance point of the instrument. It's not yet the measurement. The instrument does something with it, right? But that is then for later, yeah? So just go through those so that you at least have a bit of the idea what is going on and why we do that, even if you manage to program even better. Yeah, and on the data file. Yeah, the solar spectrum is a different file.
Oh yeah, they do. But then we use they have the largest really high resolution data. 3 million images. 3 average data.
And this is for the surface.
Yes, just yes, super easy. It's not even you can get that, or you need to request it. Can you request that data? Level 0?
No. So they need to run sea level. And then they go that calculator. No, the level 0, like, yeah, we need to run throughout the different standards to see things.
You can what is one do, it's not the same.
The level 1 did available something like 5 yeah. I think all the data of the standards are even though. Yes. Yeah.
Not NASA. You need to find CPS. Yeah, that's it. It's, I think we should look into it. Oh. I don't know. It's a
You use it from you central conference investing.
Yes.
I have a question. So
Sure.
where does this X section come from?
Cross sections,
Yeah,
X section,
so it's kind of the
the
measurements or
combination. Each line, each absorption line, you have certain parameters which describes its absorption, like the line intensity, but there are also quantities which describes the widening of the line, the profile may change a bit. All that is in a big database. And this database comes from a combination of models, so solution of the Schrödinger equation finally, and measurements, a combination of both. And what I did, I used the database.
yeah.
I've calculated using certain models the cross sections for you for the atmosphere as it is provided.
Okay, so for instance, for the remote sensing atmosphere project, does it already provide this X section, or we need
No.
to? Oh,
What I normally do when I work with data interpretation, I have a huge lookup table where I calculate the cross sections for the most important parameters, which is pressure and temperature. It's a huge lookup table. And then you have an observation over this place here. I go to ECMWF, ask there for what was the pressure there, what was the temperature, and I extract those data then from the database.
okay, so this database is kind of the generic database, or?
That's a generic database. Yeah.
So all the cross sections comes from this lookup table, or?
Yeah. It's a huge thing. I think 8 gigabytes we have. So you need some space really to process then the data. But it's general in that sense. You can apply it then to each situation.
Okay, it's as long as you have the pressure and the temperature
Yes.
data, and you can have this cross section.
Yeah.
And then we can calculate the, let's say, optical depths.
Yeah. Assuming the atmospheric concentration.
Yes, of course, yeah, atmospheric concentration, or like trace gases concentration or density.
Yeah.
Yeah, and then we can calculate the optical depths.
Yeah.
And then if we know the solar irradiance.
This is, some instruments even measure the solar irradiance. So, so as you know, the Trabomi on S5P, yeah, when it comes from the eclipse, it points one time to the sun to measure the solar spectrum. And then it measures downwards again later to see the Earth shine reflectance.
So it means that we can also use this kind of irradiance from the measurements itself.
Yeah. Other instruments, they do assume that it is already measured and you can use it from a model, from such a file. So that is a bit a certain choice.
Okay.
Yeah.
Yeah. Okay.
So there is a file here,
Yeah,
and that is
yeah.
a standard solar spectrum.
Okay. So this
Yep.
hybrid reference
Yeah,
spectrum.
yeah,
Okay.
yeah. Because in the solar spectrum you
But it's
have
only for one day, right?
the solar spectrum is pretty constant. I mean, the sun doesn't change much. A bit with activities, but that's not so important. Yeah.
Okay. Yeah. Thank you.
Yeah, sure. Yeah, just want to come to you. Yeah,
So I cheated a bit.
that's
I was
fine.
just trying to understand.
Yeah, that's good.
Is this for the surface or is this at the instrument? Because it's just one-way transmission through the atmosphere.
The transmission total is already the combination of the solar part and the viewing part.
Oh, okay. So
if you look there, you can go where it is defined. That was the total, but if you go down, I think I redefine it. I hope at least.
Oh, maybe I didn't. I don't think I did.
Maybe.
That's possible, but it's
But in principle, that should be the case. So you get
Yeah.
then a cosine,
Yeah.
1 over cosine,
Yeah.
to correct for the slantness.
Okay.
Yeah.
Yeah.
I hope that I didn't forget that. It looks like that I forgot it, right?
Yeah. Because here it's yeah.
Where's the solar singular angle? Can Emily? Yeah, do I know that?
I don't think this one is used.
Oh yeah, but actually you should. Then it's my mistake.
Okay.
Yeah, sorry for that. Yeah. So we come to the end, and I understand that we may not achieve the final spectrum, but maybe you have some time later to do that. But I want to discuss one last point. As I said, what you have simulated so far is not the observation itself. It is something which describes the light at the telescope of our instrument. And then what happens with that light? All these different wavelengths, they all come together in that instrument. We need a kind of dispersive element in our instrument. It can be a prism, it can be a grating, whatever, yeah? And what it does is that it maps now this light on a one-dimension of our detector. So different colors, different wavelengths come on different, are mapped on different positions of our detector, right? However, this is not perfect. It mixes color a little bit. That is what we call the spectral resolution of an instrument, right? So it cannot measure the physical lines as they are, but a kind of blurred spectrum. Yeah? And this blurring is a function which you always have to measure on the ground before you put the instrument somewhere in space, at the ground, wherever. Yeah? So there's what we call non-ground calibration, where you exactly measure how this blurring works. Yeah? And this is something we do here when we say this mixing is described, where is it? By the instrument, yeah, here, by an instrument spectral response function. It is just a blurring function here, Gaussian, which blurs the spectrum and so describes this mixing of light in our instrument. Yeah? So what you have to do finally is to convolve your spectrum with that response function. It's a simple convolution. Therefore, you use the SciPy convolution. It's easy, quick, and provides us then the spectrum. And doing so, and that is really then the final picture. You have here the physical spectrum in light gray with all the lines, right? That's the physical spectrum at the telescope. But after that, you convolve it and you take the values at certain points which belongs to the spectral position of our detector element. And that is our observation, right? These numbers, these crosses, those you can compare with the data set coming from the satellite. And what will happen? It will not agree, right? Because your assumptions on CO2, on the albedo, on water vapor, on methane was wrong. And then you have ways to adjust your assumptions on the atmosphere to bring your model into an agreement with the observation. This is called inversion theory. That is typically applied. And if you achieve an agreement between your model and your observation, whatever, you define a certain threshold of quality, and if you achieve that, then you say, okay, now the numbers that I've used in my forward model to simulate the observation, they represent what the atmosphere was for my observation. That is called retrieval, actually, or data reduction sometimes. Yeah. So if you have time, still do at the last step this convolution, then you already what we call a forward model, a model which simulates the observation, and then in an iterative loop, these are adjusted, the inputs are adjusted to bring model and observation into agreement. And that's what we do at huge computer facilities, because a lot of data needs to be processed, as always with satellite data. And those are the data you then finally see when you look at NO2, at methane. I've heard S5P tribomi, the methane product is a famous one, CO. We all do things like that. Yeah? Shall we close it with that? Yeah, good.